Hello, seventh graders. Continuing with our area formulas. This is video number 3B. In the first video, we talked about rectangles, both perimeter and area. We looked at a little algebra that can help us in this area. Many of the things you learn in math are connected in ways that you might not be able to appreciate now, but later. And I tried to give you some appreciation for that connection at the beginning of the last video. Looking at, for example, how if you have 3x times 2x, that would be 6x squared. Well, if you have a rectangle that's 3 inches by 2 inches, in the very same way, you can do 3 times 2 is 6, inches times inches is inches squared, so you get the desired result of 6 inches squared, or 6 square inches, for the area of such a rectangle. The algebra supports the geometry, and this kind of thing in math is everywhere. So we've kind of gotten through the rectangle. We're going to look at a square, which of course is a special kind of rectangle. Then we're going to go back to the more general parallelogram. A parallelogram is more general than the rectangle or square, but we actually start with the rectangle in terms of understanding area. It's sort of our definitional beginning, that the area of a rectangle is length times width or base times height. We then go back and show how we can understand and agree with the formula for a general parallelogram in terms of the rectangle. We're going to do that in this video. But first, a look at the square. And after we deal with the parallelogram, we will go on to the triangle. In this diagram here, I'm inconsistent with my labeling. I used a print S here. And rather than redraw this whole thing, which I did first, you can see back here I used a script S for the side of a square. And the script S actually has an advantage because it doesn't look like a 5. But rather than redo the diagram, we'll go with this. All of these are S's here, not 5s. And of course, the perimeter of the square would be S plus S plus S plus S, but that simplifies to 4 times S. And because the square is a rectangle, its area is length times width or base times height, but the length and the width both happen to be the same, and I'm calling them S. So the area of this square is S times S, or S squared. Now let's look at a specific square, one which has each side being 7 centimeters. Well, you should be able to tell me pretty quickly what both the perimeter and area are for this square. Add up the 4 sides, or use the formula. If you add the 4 sides, 7 centimeters plus 7 centimeters plus 7 centimeters plus 7 centimeters is 28 centimeters. But you can take a shortcut and do 4 times 7 centimeters. Let me just do that from the formula, 4S, right? And here S is 7 centimeters. And 4 times 7 centimeters is 28 centimeters. And again, in terms of the connection with algebra, if you had 4 times 7x, 4 times 7x is 4 times 7 times x, 28x. And we can approach this the same way, just treating that centimeters as if it were an x. And continuing with that here, the area of this square, according to the formula, is S squared, side squared. Well, the side is 7 centimeters, not just 7, but 7 centimeters. So let's put it into the formula that we just looked at, 7 centimeters squared. Okay, now how can we think of that? What does it mean, 7 centimeters squared? It means 7 centimeters times 7 centimeters. That's what it means to square something. And again, please don't think of the side here as just being 7. It's 7 centimeters, and the units work out the way they need to. 7 centimeters times 7 centimeters. As I did in the previous video, let's think of this the same way as we think of 7x times 7x. That would be 7 times 7 times x times x. Just rearrange the numbers in that way. And then we would get 49x squared. Well, here we get 49 times centimeter, 49 centimeters squared, right? 7 times 7 is 49, and centimeters times centimeters is centimeters squared. Okay, now you can read this as 49 centimeters squared, but you can also read it as 49 square centimeters, and you can write it out in words, abbreviating the word square, 49 SQ centimeters. All right, and what do we mean by centimeters squared or square centimeters? We mean a square where each side is 1 centimeter. And going back here, now this, I constructed one of those right here. This square here, this is not a square to indicate a right angle. All of these are right angles. But what this square is here is a square centimeter. I measured 1 centimeter this way and 1 centimeter that way. I'm not going to draw all 49 of them, but you can easily imagine you've got 7 of these squares going this way and 7 squares going up that way. So you don't have to count them all. You do 7 times 7 to get 49 of those square centimeters. So that's the square. Here we have a rectangle and a parallelogram. We actually have 2 parallelograms because rectangles are parallelograms. They are special kinds of parallelograms. And I constructed these 2 parallelograms, the rectangle and the parallelogram, in a certain way. They each have the same perimeter because just as with rectangles, rectangles have opposite sides being the same length. So even though I didn't label it, this side is 4 inches labeled, this side is also 4 inches, this side is labeled 3 inches, this side over here is also 3 inches. We talked about that earlier. And in a parallelogram, opposite sides also have the same length. We don't generally talk about with parallelograms like this, which are not rectangles, we don't generally talk about length and width. And maybe the reason we do that is because the area of this parallelogram down here, this is the important lesson here, the area of this parallelogram is not 12 square inches. In fact, it's a lot less. The perimeters are both the same. I want to just make that point now and then move on to area. The perimeter here would be 14 inches, right? If you add up the 4 inches, the other 4 inches, the 3 inches, and the other 3 inches, it would be 14 inches. The perimeter of this parallelogram is also 14 inches because you've got 4 inches up here and another 3 inches over here. Okay? Same perimeter. Now, the eyeball test should tell you that the area of this parallelogram is much less than the area of that rectangle, even though they have the same perimeters. One way to think about this parallelogram down here, go up to that rectangle and imagine all of the sides are on hinges. They can pivot, all right? And if you were to come up here in the top corner and sort of push down this way, causing this side to move over, or actually maybe you'd have to push up from this way. Push up this way, causing this side to go over that way, this side to come down like that. You can imagine pushing the sides toward each other and they pivot on these hinges until you get something like this. Now, as you're doing that, just intuitively, you're pushing down and reducing the area. Okay. So the area up here, as we know, is 12 square inches of this rectangle. This one here appears to be much less. How do we find the area of this parallelogram? Well, the answer to that right now is we don't have enough information. We need something else. Here is what we need. We need the height. Okay? Remember, the formula for a parallelogram is base times height. And I intentionally did not draw the height in here, but now I'm going to. The height of this parallelogram can be represented like this. And remember, the height has to be perpendicular to the base. That dashed line there is the height of the parallelogram. It's the distance between this base here and the opposite side. Let me label the 4 inches now the base. And this dashed line that I just constructed is the height. And it happens to be, I constructed this parallelogram this way on purpose, it happens to be just 1 inch. That height, which is that dashed line. Now the dashed line is not one of the sides. It's a line segment that's inside the parallelogram, but it's the height. Remember the formula for the area of a parallelogram? Base times height. 4 inches times 1 inch is 4 square inches. This parallelogram actually has 1/3 the area of this rectangle. Because this one is 4 inches times 3 inches, this one is only 4 inches times 1 inch. Now, when I'm teaching this topic of the area of parallelograms in school on a whiteboard, I often will say, imagine taking a pair of scissors, if this parallelogram is on a piece of paper, cutting along that dashed line, and then doing something with the 2 pieces. But since this is a piece of paper, I can actually do it. So I'm going to pause and use scissors. And here it is. By cutting out the parallelogram, I lost the labels on the sides, but down here we've got 4 inches the base, and over here is the other. This up here is also 4 inches. We've got 3 inches on the left and 3 inches on the right. So what I'm going to do is I'm going to cut along the dashed line, which is the height. Okay, that's how the parallelogram was. And what I can do is bring this triangle over here. It's kind of like magic trick. I'm not trying to hide anything from you though. There it is. What do we have? We have a rectangle. Looks like my diagram wasn't perfect. It should fit in here exactly, but it's close enough for you to get the idea. We now have a rectangle. Okay? Now, this up here is the base. Okay? It was actually, the way I drew it, it was the side up above the base. The base was down here at 4 inches. This also here, the opposite side, is also 4 inches. And now look at down here at the original base. I'm cutting that base into 2 pieces, but then I'm moving this one, just moving this one over here, so it's still the same 4 inches. So now what do we have? A rectangle that is 4 inches by 1 inch. This height here now becomes the side of a rectangle, and the same over here. This is also the height of 1 inch. It is a rectangle that is 4 by 1, and that is why it has exactly 1/3 the area of this other rectangle up here that was 4 by 3. And you can kind of see that now. I could put another one of them here in the middle and then a third one up here. 3 of these new rectangles would completely cover the one up here. This one is 12 square inches, and this one here is 4 square inches. Because again, going back to the way the parallelogram looked at the beginning, base of 4 inches, height of 1 inch. It is equivalent to the rectangle that's 4 by 1. And let me just repeat this important thing. Base and height are always at right angles. This is not the height of the parallelogram. This 3-inch side over here, it clearly does not meet the base at a right angle. That's not a right angle. But this is a right angle. This line segment here is the height of the parallelogram. Returning now to our sheet of formulas, the last one to deal with is the area of a triangle. The area of a triangle is 1/2 times the base times the height. And you know by now that if you multiply a number by 1/2, we got base times height here times 1/2. Multiplying by 1/2 is equivalent to dividing by 2. So this is also the formula for the area of a triangle, base times height divided by 2. Either one, these are equivalent mathematically. What we're going to do now is look at 3 different triangles. And the bottom line about this is that when we're looking at a triangle and we have the base identified, there are 3 possibilities for the height. The height could be another side of the triangle. The height could be inside the triangle, like it was on that parallelogram we just looked at, or the height could be outside the triangle. Those are the 3 possibilities. And in order to explore how the area of triangles works, I've decided to do this. All 3 of the triangles we're going to look at now have areas of 6 square inches. They're all going to have areas of 6 square inches. Let's look at this first. This is a right triangle. This little square down here tells us that this is a right angle, a 90-degree angle. So this, if we see this as the base, the 4 inches down here, B equals 4 inches. This side here, the 3-inch side, is the height. Why? Because it meets the base at a right angle. Consider this. Think about this way. Isn't this half of a rectangle? Imagine a rectangle that's 4 by 3. I actually had one of those a little earlier. That was 12 square inches. Well, you're cutting along the diagonal, and you're making 2 congruent, perfectly identical rectangles, one here and another one up here. This 2 identical triangles. This triangle down here is exactly the same as the other triangle that would be formed from the rectangle. So this triangle is half the area of the rectangle. This is this base times height divided by 2, or 1/2 times base times height. So plugging into the formula for a triangle, we get that the area is 1/2 times the base times the height. And here, again, this 3-inch side over here is the height because of the right angle, right? Now, let's do 4 inches times 3 inches first. That's 12 square inches. But then we have to take half of it. 1/2 times 12 square inches is 6 square inches. It's half of a rectangle. That's 4 inches by 3 inches. Its area is half of 12 square inches, 6 square inches. Pretty intuitive, pretty straightforward. But now, ladies and gentlemen, what about this triangle? Well, this is not a right triangle. None of the angles on the original triangle are 90 degrees. In fact, they all are acute. This is an acute triangle. All 3 angles are less than 90 degrees. We're going to consider this side down here to be the base, 4 inches, just like with the other one. B equals 4 inches. And the way I constructed this triangle, if you take from this vertex here, from this point of the triangle, if you drop a perpendicular line down, line segment down to the base, and notice I put the square here. This is not one of the angles of the triangle, but it's the angle where the base meets the height, and it's 90 degrees. The base and height always have to meet at a 90-degree angle. And the way I constructed this dashed line is 3 inches. I don't really have to show you the work here because it's the same as the work on the previous one. 1/2 base times height. 4 inches times 3 inches is 12 inches squared, but we take half of that to get 6 square inches. So the area of this triangle is also 6 square inches. We can't quite see it as half of a rectangle. There are ways to prove that this works just like the earlier one, which was half of a rectangle. We can show that it works. For now, I'm just going to go by the formula. Base and height, the area is 1/2 times base times height, and we get a 6 square inch triangle. Maybe the eyeball test works, maybe you are, kind of okay with the fact that those two triangles have the same areas. If I constructed them well, they do. They have the same area of 6 square inches because they each have a base of 4 inches and a height of 3 inches. This, by the way, is the case where the height is inside the triangle. The first case that we started with, the height was one of the sides. Here's the third possibility, where the height has to be outside of the triangle. If we see this as the base here, 4 inches, the height has to be the distance from this base to this vertex up here. And that distance has to be the distance between a point and a line segment, or the distance between two parallel lines. That distance has to be a perpendicular line. That's the only thing that makes sense for measuring distance. So what we have to do here, I've actually, I don't know if you can see it, I've got a pencil line going across here. We extend the base. Now, the base is really just the 4 inches, but we have to extend it in order to construct the height. And I extended it with that pencil line. So now what I will do is drop a perpendicular line segment from the opposite vertex down to an extension of that base. So I'm doing that now. I extended the base with a pencil line. And again, this height is not part of the triangle. It's not one of the sides of the triangle. See, I dropped it from this vertex down to an extension of the base. Let me put the little square there to indicate that it hits that extension of the base at a right angle. And can you guess how long that height is? I did this on purpose in constructing this triangle. It's 3 inches. That is the height. So once again, it's not necessary to show any work because the work is the same as the others. The area of this triangle is 1/2 times the base times the height. The base is 4 inches, the height is 3 inches. 4 inches times 3 inches is 12 inches squared. Take half of that to get 6 inches squared. All three of these triangles have an area, and it might be hard for me to hold up all three at once. Let's see. Okay, all having an area of 6 square inches. I think we're going to go 3 videos. This is a fairly short one, just about 23 minutes now. We'll stop this one and we'll go on to a 3C because I want to show you, prove to you that those 3 kinds of triangle area problems, one where the base and height are both sides, a right triangle, that's the starting point, that's the easy, intuitive one. The other two, where the height is inside or the height is outside, I want to show you that those two are in fact equivalent to the others. I didn't really prove that just now, but I want to provide you that proof. It's not going to change the formula. The formula is always area of a triangle is 1/2 base times height, but we'll look at why.